I'll resume where I left off on Monday, except that I'll recap a little bit because I just wanted to remind you what a kernel estimate of a probability density looks like. So we stress the probability density because it's a relatively simple thing. It probably isn't the quantity that we're most interested in economics or econometrics, although there's been interest in income distribution, for example, and so people have computed estimates of the probability density of income. But the main reason for beginning with it is because it's relatively simple and the ideas for density estimation extend to more complicated quantities that are of more practical interest. So here we have observations xi, these are scalar observations, n of them, and we're estimating the probability density of a point x, a single point, although in practice we would want to estimate the density at many points. So we can build up a picture of the probability density. So x is a particular point of interest here. The kernel function, I'll just remind you a bit about how we might choose that. But it's, I think I drew some pictures of that last time. That might be a probability density itself, actually like a normal density, but it doesn't have to be. And A is the bandwidth number which we have to choose. We have to choose the K function and the A bandwidth, and I'll say more about this topic later on. Well, I think I need to talk about this again. These are some examples of the K function, and actually they're all probability densities themselves. Obviously this is the normal density, but they don't have to be. They would normally integrate out to 1, but it could be negative sometimes. You might have reasons for choosing a K which can take negative values. So that's our definition of the kernel estimate, and the kernel has to integrate to 1. And that's almost as far as, that's as far as we've got. Now, of course, with economic data, often we're concerned with several related variables, more than one of them, and so we want to extend this idea, and so I'm considering now some extensions of the kernel density estimate, and so we think of now a function defined on the RD, the d-dimensional real space, that again integrates to 1. And to be very general, I'm allowing now for a matrix valued bandwidth, which is positive definite. For the scalar case, it just has to be positive. Now, this is more generality than we need, because in practice it would be quite difficult, to choose a general d-dimensional positive definite matrix. So in practice we would specialize. We might actually choose AD to be proportional to the identity matrix, so just one unknown bandwidth. I'll say more about that. In general, it can be a matrix. I was wondering whether I should stand here mostly or because I have to come back here to operate the machine, and maybe it's best to stay here mostly. Well, yes, so the kernel, the d-dimensional kernel function could be just a product of the same kernel function. So the UJs are elements of the vector U. Because again, it's hard, why would we want to choose different, different kernels? As I mentioned last time, the kernel function tends to be not so important. There's not so much sensitivity to it. But there are some reasons why we might sometimes not want it to be like a diagonal matrix. There we've got the case of a diagonal matrix where the diagonal elements could vary across the diagonal, but they may not. They may all be constant. Okay? So I've mentioned the constant case down here. And actually, I mentioned this is the constant case. I say for stationary time series, that's because in that case we would be, as I mentioned last time, we might, the d-dimensional vector might be a vector of values of the time series at different points. Like, for example, if d equals 2, it would be the time series at time I, and time I plus 1, let's say. Now, if it's stationary, the variance is constant. And actually, one rough way of thinking about how large the bandwidth should be is that the larger the variance of the variable, maybe the bandwidth should be larger. And we'll explain a bit more about that, because really we want to capture perhaps more information if the variance is high. So we have to do that, we have to spread things out a bit more. Right, so that's enough about the multivariate density. But estimating it, I mean, what I'm doing is I'm sort of going back through some of these aspects of interest that we had on Monday, and where we defined the functions, but now we're talking about how we might estimate them. And so I don't think I have to motivate too much how we, why we would be interested in a conditional probability density function. Again, I'm being quite general, so we've got a vector, a p by 1 vector 1, and a q by 1 vector z. It may be that p and q are both 1, all right? But being a bit more general than that. And because the conditional density is the joint density divided by the marginal density, it's natural then, since we know how to estimate a joint density, to just plug in the estimate from the basic formula for conditional density, as is stated on the right-hand side. I mean, there's not really a more clever way of doing it than that. By the way, please stop me if you have any questions. I'm happy to answer any questions. All right, yes?
In terms of like multi-dimensional, in practice, how big we can go?
Yeah, well, not very big, I think, because the problem is that you need much more information. The higher the dimension is. Actually, I've got the whiteboard here. Maybe that's a bit better for writing on. Let's try it anyway. And I haven't really talked yet about the the issue of how if you imagine you've got, let's say just in one dimension, you've got data where the crosses are, okay? And let's say we want to estimate the density. I won't put these in, but let's say we've got a greater frequency near the middle, perhaps, and it's hard to represent that. So the actual density might look like this, okay? All right, so we've got more observations in the middle. We don't know the density, we want to estimate it. So imagine we want to estimate it at a particular point. We can change the color a bit. At a particular point like here, well, basically, if you imagine we were using that kernel function, just a simple one, minus 1 to 1. This is our k of u function. So it takes the value half, or integrates to 1, therefore. What you have to think of then is that well, it's almost the same as this, but the notation is different. But we have to choose points around here. It's the point z, and zi here, at a distance a, basically. So we think about, let's say, we would choose points like here, and so the distance between there and the central point would be a, and likewise here. Okay, this is just to give you an idea. Now, similar principle when you're in more than one dimension, but of course okay, the point is this, that we're going to get a bias, actually, here, because some of these points, are actually coming from different points from the one where you're interested in estimating. But you only have negligible information actually at that point. You may have no observation. It's a continuous random variable. If it was a discrete random variable, it'd be, different matter like binomial or something. So you have like a bias. So you're trying to estimate things like up here. You probably get an estimate like about that. If you choose a smaller, then you probably get less bias because they're centered more on the point of interest. On the other hand, the more points you use, the more precision you get. Obviously, the larger the data, the smaller the variance. So there's a trade-off here between, which is influencing the choice of the bandwidth A. If we choose it too small, we won't have enough information to get a large variance. If we choose it too big, we may get large bias. Right? And this can be formalized by looking at mean squared error. But the point is that if you're worried particularly about the issue of variance, you want a reasonable number of observations. When you get into like 2 dimensions, really, you imagine, let's say you have a scatter of points here. Well, it'll often turn out, so you're interested in estimating at some point here in 2 dimensions. So you're going to have a sort of a window around there. And it turns out that really, as the dimension increases, really you need a lot more information. It's almost like exponential. So people don't often compute these things for large dimensions, more than about 3 or 4, maybe. So I suppose, in principle, sure, if you have enough information, if you've got, hundreds of thousands of data points, you can do it. But I guess it's an example of the curse of dimensionality, all right, which is a term that is often used in statistics. Things become very problematic when the dimension is high. But I think for econometrics we have to consider the possibility that we do have a large number here of, this is talking about regression now, the same principle, more than 1 or 2 explanatory variables, because that's the issue now with the regression estimation. we're trying, if you remember, we interpreted the regression function as a conditional expectation, where we can choose whatever variables to condition on we like, actually. They may not necessarily be the ones we might end up with if we were doing a parametric linear regression, but the point is that the conditional expectation, you know, is always defined, at least so long as the integrals exist. So, you know, we could just, even though we might think that there are more than one z's involved here as regressive, we could just, you know, do it with one, you know, regard that as like a predictor. Anyway, well, I don't know if we really need my kind of explanation of how the kernel regression estimate arises, but essentially, I'm sort of saying, I mean, this is, you know, like an artificial step, it's true. F of z is 1 times f of z, and the expectation of one given z is 1. So we can write this formally. So you could regard, therefore, f hat of z as, if you like, you know, we just put a 1 in there, and that doesn't change things. We don't need to put the 1 in. Which suggests that more generally, actually there's some benefit in this particular way this PC works, because I can sort of have bits of 2 slides. It sometimes may be helpful. So it is here. So if you think about for a general function of xi, and here we're being very general because xi includes both y, the dependent variable, and z, the regressor, or the independent variable, or explanatory variable, perhaps I should say. But in practice, g of xi might well just be yi, okay? We talked a bit about special cases here. So analogously, then we can think then that statistic, and this is not a proof that these are good estimates. The proof has to rely on asymptotic statistical theory. I'm just trying to motivate in an intuitive way why we might be interested in these quantities. So anyway, you know, by the same argument, you could say that this quantity could be used to estimate h of z times f of z, where h of z is the conditional expectation of g given z, all right? So, therefore, the point is we've got an estimate of h times f here, and just above, we had an estimate of f of z, sorry, must be saying z, not z, but an estimate of f of z there. So the thing is that we're not really interested in this quantity, we're just interested in estimating h of z. So what would we do? Well, obviously we would divide this, you know, after putting hats on here, or rather, we'd have the estimate of the numerator divided by the estimate of f of z, so we get a cancellation, at least, you know, approximately in the limit. So that's it's a bit cumbersome in some ways, but it introduces some technical problems. But this is the estimate. So, you know, in other words, we've got the second quantity that we came across in the numerator dividing by the density estimate. you can actually motivate this also in terms of minimizing a certain sum of squares criterion, but I don't really think that's terribly helpful. Some people, mention that, but the problem with that definition is that you do then require a non-negative kernel function, and it need necessarily be non-negative. So this is by no means a proof of anything. It's just a way of developing things, and I guess my presentation in some ways is very general. I mean, this is kind of, to some extent, based on a paper I wrote at some point in a fairly general framework. But we often don't, we could specialize, as I say, with respect to the kernel function and the bandwidth. But there's some advantage in having a general property. And this is a generalized form of what's called the Nadaraya-Watson kernel regression estimate. It was a paper back in, I think, around 1967, perhaps, in the Indian journal Sankhya by Watson, and then another paper by Nadaraya, which is in a Soviet journal, which came up with a similar estimate. And it's probably overall the most popular estimate of non-parametric regression still. There's a kind of extended form of kernel estimation that I will mention, which perhaps is maybe more widely used, at least in the statistics literature nowadays. But I think in econometrics, kernel estimation still seems very popular. Although there's also other methods like series estimation, which is popular in some quarters. Well, I mentioned derivatives. We might sometimes want to estimate derivatives. And if we use a smooth kernel, and the only one of those three kernels that I mentioned as examples is always smooth, always differentiable, is the Gaussian one, and it's possible to construct any more. The other ones had a finite support, so like the uniform one, it's continuous, indeed differentiable everywhere except at the end points. So you can't, strictly speaking, you have to be careful with it. So let's just suppose the kernel is smooth. Oh, and incidentally, I'm going back to the scalar case here, all right? So sometimes I like to introduce the notion of, dealing with a multivariate vector, multivariate variables, but not always. But obviously you can extend this idea if you want. So here we've just got the scalar case, and imagine if you choose an obvious thing to do to estimate the derivative of the density is to start off with an estimate of the density and then differentiate it, so long as the kernel is smooth. You just take the differential operator inside the sum, you differentiate, and you're using the chain rule here. So you're differentiating with respect to x. You've got an a in the denominator, so if you remember the chain rule, you're going to get a 1 over a here coming out, as well as the 1 over a, which was there. So you get a 1 over a squared. K prime then is just the derivative. Okay. Thank you very much. Thank you. Okay, so that's our estimate of the derivative. And, well, I mentioned the vector case. I just state without any discussion really how you'd estimate a partial derivative when you've got a vector. So we go back to our definition of the joint multivariate probability density, and we can obviously partially differentiate that so long as it's smooth enough. All right, so I mentioned an extension of kernel estimation that is popular in statistics. It has been now for, what, maybe 50 years or more, I'm not sure. Local polynomials. And actually, this is I mentioned that there's another way of motivating the kernel regression estimate. I did mention it before, but let me mention it now. Let's suppose that you look at this kind of weighted sum of squares criterion, all right? So it's a bit like, ordinary least squares, or weighted least squares, if you like, although the k's don't have any kind of variance or 1 over variance kind of interpretation. H here, the idea is you minimize this over H, and you get an estimate of H of Z, okay, which is the conditional expectation. And that makes sense as long as you choose a non-negative kernel, because the kernel can sometimes be negative, and we'll to talk about the possibility of negative kernels that can sometimes be negative. We have some problems there, so it has to be non-negative. So if you actually do that, if you differentiate with respect to H, you will come up with our kernel regression estimate that we had before. I won't bother to go through that for you because we have another derivation. But if you look at this, this might suggest a more general class of estimates. If you think about now putting in another term here, in addition to the minus h, a kind of linear term. So it's a term in, you notice we had this argument, little z minus big Z over A. S is going to be treated like something we minimize over. So this is just S multiplied by the difference between big Zi and little z. So it's like you're saying, with the first definition, you're saying, well, this is like based on the notion that the density, the regression function is approximately constant around the point Z. To be a bit more general, you could say, well, it needn't necessarily be approximately constant. It could be approximately linear, all right? So that's allowing a bit more generality. So it makes some sense. You think, well, maybe there's some advantage in that. So we minimize this quantity over both H and S. So, these are just the partial derivatives with respect to H and S. I don't think I need to talk about the derivation of those. I hope the formula are correct, but you can always verify them. But the idea is, as usual, what you do then to get a minimum, or you hope it's a minimum, or you can check that, if you equate the derivatives to 0 and solve things out, you get a kind of formula like this. So it's more elaborate. You've got a 2 by 2 matrix. On the right-hand side, you have to invert, and then you multiply that by a 2 by 1 vector. So, just to talk a bit more, again, I'm just trying to motivate things intuitively. I'm not giving any proofs that these are a good thing to do in a rigorous way at this point. In fact, I'm not. In terms of the asymptotic theory, whereas I say, I'm not going to give proofs, but I'm going to give conditions and states of results. I'm going to focus really on kernel estimation, not on, this extension, just because it's just too much detail otherwise. But, things are going to get more complicated here. But the ideas do go through quite simply. So just talk about the intuition. So, basically this is our regression model, all right? yi is the conditional expectation of y given zi plus an error. And incidentally, again, this error might not necessarily be IID, independent identity distributed. It could have, for example, the variant, it'll have conditional expectation 0 given z. Because if you take the expectation of yi given zi there, that's precisely this. So that conditional expectation must be 0. However, this could have a conditional variance given zi, which depends on z. So it could be heteroscedastic. This is why I was saying before that the choice of zi may not be the ideal one in terms of all the information, but it's legitimate to do this, to consider some kind of predictor of a dependent variable based on just maybe one or two quantities that seem relevant. This could be useful. Anyway, let's think about approximating h around the point z. Around the point z, little z here. A Taylor approximation, all right? So where we say, well, this is h of, we've just approximated this term by h evaluated at little z plus then the next, just one more term, s of z times this linear term. So this is like really the derivative, of course, of h with respect to z, okay, from the Taylor theory.
It's like you expanding.
Yes. But
using like the first order.
Yes, exactly. But it's just an approximation because there would be other terms, of course, in general. But you're saying, well, maybe this linear term is important. So this is our s of z. It's the derivative of h with respect to z. So, and of course, this derivative is something we might be interested in. I just talked about derivatives of density, probability densities, didn't I? Multivariate densities. But you could be interested in the derivative of the regression function because, for example, if it's approximately a linear function, then the derivative will be approximately constant, and that's of interest. So what's happening here is that we're getting, at the same time, so to speak, estimates both of h, the conditional expectation, and of s, its derivative. And this could be, quite valuable because it's all in one kind of step. So you get different results, of course, from, as far as estimating h, than if you looked at just a simple Nadaraya-Watson estimate, but they will both estimate the same thing. And this is a bit simpler. And actually, there's a sense in which you get less bias using this approach, potentially.
Because there's some correlation between.
Sorry?
The reason why you get less bias.
Yes.
Bias is getting both at the same time.
Well, because you get less bias for the HS, and partly because of this way, the fact that you locally approximated it here, the linear thing will more often be a good approximation. That's why. Of course, that's only if really h, to be a bit fussy here, is really only if h is differentiable. In general, you may not have to assume that, in order for this argument to make sense. So this is a very popular method. I mean, I've used it a bit in my research, not a lot, but it's, as I say, it's not greatly used, I think, in econometrics. I think it's, but it is quite popular in statistics. So that, you know, I think it's worth introducing that because it might be something you come across if you read more on this kind of literature. And in fact, we can extend the idea. I mean, I don't think people very often go beyond the local linear estimate, but you can have a local polynomial estimate where you, in effect, you do a Taylor approximation of a higher order. So you get the, here's the linear term, and then you've got a term of order little n, tau little n. And so again, it's a simple matter, really, to write down the estimates of all these S's. They all have interpretations. I didn't bother to write it down, but it's the same principle, and you just differentiate partially with respect to all these things and solve out. And this is kind of, again, should be better if you have greater smoothness in the function. So I'm stressing kernel estimates in the notes here because they are somewhat simpler than these local linear or polynomial estimates. When I come to talk about the theoretical properties, things are quite similar, but there's great complexity, and I think we have enough complexity. So still, I think ordinary kernel estimation seems to be the most popular method in econometrics. It's referred to an awful lot. Well, I wanted to just to mention another method which I'm not going to really discuss in detail in terms of its statistical properties, but I think it's good to place things in some perspective. Because actually, as I said, this Navarayan-Watson estimate is rather cumbersome, because it's a ratio, not very intuitive really, or except if you think about that interpretation as a minimizing a weighted sum of squares. But we're just going to talk about estimating the conditional expectation here. Well, if you were approaching this subject without, any prior sort of background at all, being influenced by knowledge of kernel estimation, you might think, well, you want to estimate h at a particular point z, little z. Wouldn't be a sensible thing to do is to just say, well, look, let me look at the certain number of observations such that capital Z is closest to Z, all right? So just looking at the distances rather than saying, well, let's choose a certain number within a certain region that are close. So these are the nearest neighbors. And so it looks like this, h hat of z, where these weights typically are going to be either 1 or 0. You see, we're doing a summation over all observations n, and the weights add up to 1, and let's say they're all non-negative. I mean, strictly speaking, they can take other values than 1 or 0, but, when I say 1, I really mean 1 over n, because n is the number of neighbors you choose. So if you imagine you just want to give equal weight, you would imagine the wi is then to be 1 when you're one of the nearest neighbors, and 0 otherwise. So, just to give compare a bit with how we, what we were talking about with the kernel estimation. The idea here is, in some ways, this idea extends a bit better, I think, to multivariate data, imagine we've got these points here, and we're interested in estimating at some point there. We say, well, we want m to be equal to 6. So we choose this one, and we draw a circle, effectively. It doesn't have to be a circle, but you could have a different kind of principle, but these are the ones you use. So that's a little bit different. So we're basing it not on the actual distance, but using a certain number of closest ones. So the m is a bit like the bandwidth for kernel estimation, but it really, a large m corresponds essentially to a small a, if you like. Large m corresponds to a small a, but then 1 over m is small. So that's the kind of principle. So one advantage is it doesn't have this denominator in it, which the kernel estimate has, and it is easier to handle mathematically than a kernel estimate. On the other hand, these weights actually depend in a complicated way on all of the z's, so it's actually rather more challenging to deal with technically. But I have worked a bit with the nearest neighbour estimate, and it does have some advantages. Sometimes one can get nicer results, I think, using nearest neighbour estimation. It hasn't been very popular in econometrics or economics. One time I know it was very popular in, I think, electrical engineering. I don't know if that's still the case. But I think it's a nice intuitive idea, really. I think more intuitive than kernel estimation. Yeah.
So m is
the number of neighbors, basically, yes, that's right.
So it doesn't matter what is this m, but you can pick like let's say m is 10, so you can pick like the 10
yes.
closest to
yes, that's right. And essentially, I haven't really talked about the choice of the bandwidth A, but in terms of practice, what we would think of is here the larger n is, the larger you should choose m. Okay, in some sense. Obviously, that's very vague advice, but that's the principle. Because the more data you've got, the more the more closely compressed it should be overall, and so you should choose a larger number of neighbors. Likewise, with the kernel estimation, the larger n is, the smaller a should be, because again, the more observations you've got, they'll be more tightly packed, so you'll get more within a given small interval. But this is all very vague, but it just gives a rough idea. And unfortunately, there is a lot of ambiguity about these estimates. This is there's no such thing as a free lunch, really, and we're avoiding dangers of misspecification from choosing certain parameterization, and I stressed that last time. However, there's ambiguity here in how we actually define the estimate, but people have come up with so-called optimal ways of choosing the bandwidth A in kernel estimation, and also choosing m, the number of neighbors to choose in nearest neighbor estimation. And I will talk later about the choice of fairly sort of objective methods for choosing the bandwidth in kernel estimation. All right, so just some final remarks. If you look at the literature, you can find other methods which are discussed there. And there's the histogram, which I think many students come across in elementary courses of statistics, and that's a somewhat different idea than kernel estimation, for example, but it's related. Essentially you put things in bins. You put the data in, in the sequence of bins, and the higher the more in each bin, the higher the rectangle goes. It looks like for a kernel density estimate. This is not the kernel. Sorry, not a kernel. It's a histogram density estimate. Typically looks like this, doesn't it? So it's a bit different from the form of a kernel regression estimate, but there's some similarities. I think the kernel estimate has proved more popular in the literature, certainly the theoretical literature, and also I think the empirical literature is because it's easier to deal with theoretically. But people have actually extended the histogram idea to regression, so from regressigram and prediction to predictogram. One time there was a big literature on sort of using a kind of orthogonal series approximation. More recently, in econometrics, it's quite possible to look at series estimation, where you imagine that you're approximating the function of interest by like a sum of weighted sum of relatively simple functions like powers or something like that. And this gives another way of proceeding that has some advantages. There's also spline methods are being used too, and others. So you can see some of these things referred to in the literature. Some I think are not very popular in practice. As I say, kernel estimation is very popular. So this is what I'm suggesting here. Any questions before I go on? All right. Well, I'm afraid we have to talk about some theoretical properties. So just to make sure we know some basic properties. If we think about a parameter, and I'm not necessarily talking about parametric estimation, but because this so-called parameter could be what we've been talking about, estimating a function at a given point, just one point, let's say, like estimating f of x at some point x. Let's suppose we have an estimate, theta hat, which is, I put theta n hat there to stress the fact that we're going to it depends on n observations, all right? Now, I mentioned unbiasedness already, so here's a definition that we have unbiasedness of theta hat for theta. If the expectation of theta hat is theta, whatever the value of theta. In other words, you don't get unbiasedness if it just happens that the expectation is theta hat for a given value of theta. It has to be odd for all values of theta. And for all n, okay? But that includes even small finite values of n, and it's very rare that we can achieve that property with many statistics because a lot of them are complicated functions, and you can't take, it's not easy to take the expectation of a ratio of random variables. The expectation of a ratio is not in general the ratio of the expectations. Okay? Now, in somewhat more cases, you can say you've got asymptotic unbiasedness. So you see, you could have a situation where the expectation of theta hat exists. You could write it down, it's not theta, all right? But maybe when you let n go to infinity, things kind of simplify. Basically, the reason for stressing asymptotic theory is because things are too complicated for finite n, and things tend to simplify if you let n diverge. So here you get asymptotic unbiasedness if the expectation converges to theta. Again, it has to happen for all theta. However, for many statistics, you know, as I say, the expectation of theta hat doesn't even exist for large n. So this is a bit of a limited property, but we do have to introduce it here, partly as a warning, you know, that it may not exist, but we have a kind of a general result, which is a kind of my own extension, really, of something called Bochner's theorem. So this is, I'm looking at a function here, or an estimate here, p hat of z, where we've got something, part of this is familiar, this is the determinant of a q by q positive definite bandwidth matrix, AQ, and this is G of xi are the basic data, and as before they're partitioned to have a y component and a z component. So this is precisely as we had before. We had yi, sorry, no, xi is yi, zi. Oh yeah, maybe it's best to do that. Okay, I just thought we would. All right, let me do that then too. Just I have to switch between. So to remind you then, I think it was this one. Yes. Okay. So xi is yi zi. So switch that again. Okay, so the LQ function, and here I drop the Q. It means it's a dimension Q, same as A. This is like a kernel function, but it doesn't necessarily integrate out to 1. It can integrate out to some other number L. The reason for this is that with this flexibility, we can use this result quite a lot, you know, to help us to prove things. Even though I don't go through the proofs, it's useful to introduce this as a step. And it turns out that this will estimate. Not L times P of Z, where P of Z is H of Z times F of Z. Remember, a bit like the numerator in the Navarro-Watson estimate, except we have this quantity L. So L might be some other number like 2 or something in general. It's just to frame things in a general way. So H then, again, is the expectation of G given Z. So, for example, if G equals 1, identically 1, then H is identically 1. And P hat of Z is just the kernel density, F hat of Z, if we have an ordinary kernel which integrates to 1. But in P hat of Z, as defined in the earlier, on the previous page, we don't necessarily assume that L integrates to 1. So this is because some of the uses of the theorem we're going to have relate to situations where LQ is some function of a kernel that doesn't integrate, where the kernel integrates to 1. So for example, it turns out sometimes LQ is actually the square of K. So that's why I'm using a different notation. All right, but I'm going to suppress reference to Q and just write L for LQ and A for the matrix AQ. Okay, so this is the theorem, and I think it's useful to have these, write down these conditions, even though some of them are a bit complicated, in order to, again, provide some kind of indication, you know, for practical use, you know, things that are important, you know, some background properties that are important. And what we need here, these are quite mild conditions actually. It's very hard to say that you have, obviously we need sufficient conditions. There aren't many situations where you could say you've got a full set of necessary and sufficient conditions, because often there's some trade-offs. But basically what we need are some conditions on the random variable, okay, and also conditions on the kernel and conditions on the bandwidth. Now, the conditions on the random variable I think are the most important ones because they can't really be checked. You know, like we have at the top, conditions on H and F. Now we don't know these functions, in fact these are what we're trying to estimate. Unfortunately, you know, we have to make assumptions there. So we assume they're continuous at Z. And there's a, why is this important? Well, if we think about, try and draw a picture here, you know, to explain why the continuity matters. Suppose we have, we're estimating a function which behaves like this. It suddenly has a jump, right? That maybe at some point. So this could be a regression function. This could be our H and Z. I've done something to the lighting here. I've looked for the lamp. Let's see, I've turned it off now. Maybe it's...
Yeah, it's certainly that.
Oh, is it? I hope so. This was the thing, wasn't it? It's a bit dim still. Ah. It's a bit brighter even. Is this? I don't know. That's all right. That's okay. That's okay. I think I'll try not to touch it again. So this is our regression function. Has a discontinuity. This is something that might happen. In fact, there's a literature on regression discontinuity. However, it's a problem. So you know, this is our particular point Z. Now you can imagine we want to estimate the function here. We've got data, you know, around here, and so we imagine we choosing the closest, you know, not the closest, but you know, within the bandwidth A here. So you know, this distance is A, and this distance is A also. Well, the problem is that you see really what if we do this, what we're going to be probably estimating is something kind of in between. You know, the estimate is liable to be about there, because we're putting weight, equal weight on once before and afterwards. So, whereas the way I've drawn this is that actually the jump comes just before the point. Okay, so really this is trying to estimate this. Or, you know, if you had it the other way around, the jump was just after the, you know, you've got here, then again you'd have a kind of a bias there. So there's a discontinuity there, all right? So this is why we need the continuity. Right? Continuity is quite a mild property though. You know, we don't require differentiability. All right? So we're not making a whole load of assumptions we don't need. This is something we really do need. Okay. Switch back again. So we need that assumption, it turns out, on both H and F. Just continuous at the particular point of interest, Z, but again I should say that in practice we want to estimate the function at the whole set of points, you know, and then look at a picture of what the estimates look like. You know, then we can say, well, look, does H look at all linear in Z, for example? You know, looking at things perhaps in a, you know, in a somewhat subjective way, but you know, in a kind of agnostic way, rather than perhaps doing a hypothesis test, you know, for linearity. That's another approach, of course, you know, using Lagrange multiplier or something. You can test for linearity of regression, perfectly good, but it doesn't give you any idea of what the departures might be from that. We also need, more technically, the condition 2 that the expectation of h function of interest here is finite. Pretty mild assumption, really. Well, the next bunch of conditions, I don't want to say too much about because these are conditions which you choose the function L in practice, so you know whether they hold or not. There's no way you're going to choose an L function that doesn't satisfy these conditions, all right? So it's quite a different story from the first two conditions, which, you're assuming them, but they may not hold. You may be unlucky. But really, they're quite innocuous. We already had condition 3 that little l integrates to big L, which can be any number, any positive number. The next condition 4 basically says that L is a bounded function. Well, nobody would want to choose a kernel that is unbounded. All the examples I gave are bounded. Then there's an integrability condition, condition 5. Well, again, we said that for the kernel density estimate, the kernel would integrate to 1. So it's possible that L could be negative somewhere, and we'll come back to that issue. That's why I have an absolute value there. But again, that's quite innocuous. The last condition, 6, and I should say that what is this quantity here? This is the Euclidean norm. If I can fit this on the same piece of paper, so as to protect the planet's resources. U equals U is the vector. U doesn't matter if it's a column or a row vector. What was the dimension? Q, I think, wasn't it? The norm of, this is the Euclidean norm, basically. And so, if you want, let you write that down if you want. If you want, u to the q, you just raise that, to the power q. So what this is a tail condition, really, that as the, in general L, may never become 0. It might do. It might be like a, uniform density or something, in which case this trivially holds because eventually L will be 0. But this just says the tails mustn't be too substantial. It would easily hold also for normal density, actually. So these are quite innocuous, all right? So let's not worry about them. The conditions on the bandwidth, we have to have them, all right? Just to be, actually, it's funny though, some of the literature makes a big deal about some conditions on the bandwidth. I think it's silly, basically. I think it's, this is what matters mainly. But also conditions on the bandwidth matter because, unfortunately, these are all asymptotic conditions. And we don't really know what's going to happen ultimately, as n gets big. Asymptotic as n diverges. Now, the first one is quite easy to understand intuitively. I think I mentioned it, that as n goes to infinity, the bandwidth goes to 0. So the more data you've got, the smaller you should choose the bandwidth. Because then the idea is that you don't want to have bias asymptotically. You want the bias to go to 0, and in general, for that to happen, you really have to be centering on the point of interest. The last condition is technical, and it says that the norm of a to the power q divided by the determinant of a is bounded. Well, that's quite easy to motivate, and it's trivial in the scalar case. So let's not spend time on that one. We just have to have it. Then, we have the limit of the expectation of p hat of z is p of z times L. So we don't get asymptotic unbiasedness unless L is 1, but as I say, it's useful to phrase things in these terms. The reason why we get into the big L factor is because we've chosen a little l that integrates to big L rather than the general one of 1. Well, I've got some definitions here. This was the one we had before, essentially, so I don't really right, well, okay, I mean, that last condition is true, for example, if all of the elements decay at the same rate. Okay, so that's the result, and I'm not giving a proof of that. If you want me to provide a proof, you can write to me and I can send you one very easily. But I think it's in a fairly heterogeneous group like this, not everybody will have the same background, and we can spend ages proving so. I mean, I think it's important, obviously, to have some intuition of why we're doing this, and I'm trying to provide that. I think it's important, though, then to have some, some kind of skepticism, born of realizing that there are limitations here, and you must be in the right kind of framework for things to work. There are conditions, and these are phrased mathematically. But also, we want to actually provide some results which, show, again, give some intuition perhaps in what sense these are going to be good things to do, rather than just talking in a vague kind of way, rather like I was doing earlier on. I was trying to motivate the estimates, but not give any kind of properties. And, we have to talk about statistical properties here. One simple conclusion here then, if we choose the regular proper kernel function, so big L is 1, and we look at that estimate, so we can replace the L by a K, for example, then bearing in mind the definition of asymptotic unbiasedness, we say that f hat of z is asymptotically unbiased for f of z. So the bias goes to 0. Expectation of f hat of z converges to f of z. It's clearly a desirable property. All right? It's not the only property that matters, but it's desirable. Yeah.
Usually we prove the consistency that it converging from the...
We're going to do that.
Oh
yes. Oh yeah. No, that's much more important.
Yeah.
Oh yeah. No, and of course we must confuse that with asymptotic unbiased. Absolutely. No. Consistency is really, you could say, perhaps the most important property here for non-parametric estimates, maybe. And so we do have to talk about that. The main thing is that they are consistent, but we haven't defined consistency yet, so I don't want to get ahead of myself. But that should be coming up fairly soon. Asymptotic unbiased is a very limited property, and you see, when we talk about this kernel regression estimate, I'm afraid we just cannot talk about asymptotic unbiasedness. So the numerator will, under these conditions we've had, have expectation that will be asymptotically unbiased for the corresponding population quantity, and likewise the expectation of f hat will be unbiased for f. But unfortunately, as I said, the expectation of a ratio of functions of random variables is in general not equal to the ratio of the expectations. Something I always stress over many years to my students, who are very good generally, but always in examinations, some of them claim the reverse, get things wrong. All right, so perhaps I should just emphasize this here. general, and it's, when I say general, it's probably more often than not. Okay, so this is, you know, the general functions, let's say r of x divided by s of x is not equal, oh sorry, yeah, okay, we've got a ratio here, it's not equal to the expectation of r of x divided by the expectation of s of x. And in fact, you know, this expectation on the left-hand side may not even exist. So, asymptotic unbiased is a very limited property, but it does play a role, and that Popper's theorem in particular is useful in proving consistency, it turns out. You know, so that's another reason for doing it, and other properties too. Okay. All right, now this is another point though here. There's no assumption of the independence of the x's at all, or indeed any requirement of any, you know, falling off of dependence, which is something we will need. There will be talk about consistency, but this is something which is familiar. I mean, if you think about, you have the sample mean of some random variables, xi. What's the expectation? Well, if they're all identically distributed to the same mean, the expectation of the sample mean equals the population mean. There's no requirement that they be independent. It's just a linear operator, the expectation. You're just treating them individually. Okay, there's no, so, you know, again, this is something, you know, emphasize over the years to students that, you know, independence and identity of distribution are completely different properties. You can have one without the other. And I think it's very unfortunate in some ways that we have this abbreviation, IID. Many people just think of them, you know, as being bound together. And you must have one, you know, you must have them together. And I think they're confused by that, actually. So we don't need any independence just for this property, but it's a very limited property, you know, practice. We need it in order to develop the theory. Okay. So, all right, the higher order kernels. Now, a reason I'm talking about these is because they're quite important in some of the results in semiparametric estimation, it turns out. The point is that okay, we looked at asymptotic unbiasedness, which simply means the bias tends to zero. Well, we might like it if the bias converged to zero quickly. So that would mean that, you know, intuitively, for a given sample size, the bias would be smaller, you know, for an estimate, you know, which had a fast convergence to the bias than one that had a slower convergence. Let's look again, I'm stressing just the scalar case to get the ideas across. You can generalize all this, but it just becomes too cumbersome. And we're just looking here, the kernel essence, so we're reverting to the K notation. So that's the kernel density estimate. You know, we're just looking at the simplest situation of a univariate kernel density. And we've got a theorem here, immediately. Right, now, these are the conditions on the kernel. Most of these are innocuous. Conditions, I'll come back to condition 1 in a minute, but I want to look at these. First of all, this one, and this one. 2, 3, and 5 are innocuous. Condition 4 is the one of interest here, because what we're doing is we're going to make an assumption that f is smooth. So remember, f was just continuous in the previous result. Now let's say, well, you know, we're willing to make a stronger assumption. We don't know that this is going to be true, but after all, you know, when we assume we've got normally distributed data, you assume the density is infinitely differentiable, all right? So we might think, well, look, I want to get some stronger results, and to get these stronger results, I'm willing to impose some stronger conditions, all right? So you're saying it's R times differentiable. Again, we're just talking about a particular x point, all right? That's all. So we have this different R times differentiability. So the larger R is, the stronger the property. Now, we can exploit this in order to get estimates with smaller bias, so long as we choose the kernel suitably. And this is what we do. We choose the kernel to satisfy this property, that for each j going from 1 up to r minus 1. So let's suppose r is equal to 6. You say, well, let's choose a sixth order kernel, so to speak. This has got to be true for all j between 1 and 5. All right, well, we'll discuss these conditions more, but it turns out that as a goes to 0, the expectation of f hat x is f of x plus something of order of magnitude a to the r, all right? So that's something I guess I should define what I mean by an order of magnitude, shouldn't I, here, just to be on the safe side. Okay, so what was the I guess we'd say that let's see if S of A equals O of A to the R if S of A over A to the R is, well, let's say it's bounded as A goes to 0. This is the same kind of A, okay? So we're saying that, so it's not an exact rate necessarily, but it's a kind of up or down. So this has to be kind of fine. I think that's all right as a definition. I'll just wait a bit. So you see, the point is that if we're stressing the dependence on A here, because of course there's a dependence on X, but X is fixed, but this expectation does depend on A, all right? Because A is in there somewhere. And we're saying then that if you take off the f of x part, the remaining term will be of order a to the r. The point is that A gets small, so the larger R is the better. Okay, but eventually A is going to be less than 1, all right? Because it's going to 0. So therefore, it's going to going to 0 at a fast rate. Obviously, if A was large, the bias would be larger, if A was larger than 1. But we're concerned with as A goes to 0, so we need eventually A is going to be, of course, less than 1. Right, so, so therefore we're getting a better result in terms of bias, okay? By doing this, and we need to choose the kernel to satisfy this, and to have that smoothness. We need both of these things. If we just have the, impose the extra smoothness, but we don't choose the kernel to satisfy a condition like this, then we don't get any benefit from the smoothness. Likewise, if it turns out that actually M is not as smooth as this, and we do use this as some kind of kernel, again, we don't actually get any benefit. So we need that property holding, but also to exploit it. So, well, some of the conditions on K are not important, as I say. It's this condition here that we just had, the condition 2, no, condition 4, which is the important one. Now, the point is this, for supposing R equals 2 only, then this condition is pretty innocuous because if you, in that case, this has only got to be true for j equal to 1, because r minus 1 is 2. And if k is a symmetric function, so k of u equals k of minus u, and although there may be some reasons, sometimes people discuss kernels that are not symmetric, that's very rarely the case, and we're not going to talk about that. Usually kernels are symmetric, like the examples I gave are all symmetric. I'm sorry, I'm forgetting the microphone. I hope everybody's able to hear. A lot of sort of multitasking here that I have problems with at times. So this is innocuous, this condition, really. But if you're only choosing r equals 2, so you'll just want to say, well, r is twice differentiable, then you're not really doing anything special. You see, in other words, then you're getting a result that the bias is order a squared, which is better than just going to 0. Not much better, but it's a bit better. But let's supposing we're more ambitious, and we take r bigger than that, greater equal to 3. Well, again, symmetry can help, because if j is an odd integer, again, so long as the kernel, decay is slow enough so the integral exists, again, this will be 0. Like for, j is 3, for example, k is symmetric, it will be 0. However, what about if j equals 2? So supposing r equals 3 or 4 or something, for those cases, integral of u squared times k has to be 0. And that's innocuous. And that means, in order for that to happen, so you've got u squared is always non-negative. K, if k is always non-negative, there's no way that integral can be 0. You must have some negative region where k is negative in order to end up with a 0. And I'll draw you a little picture of that. Yeah, maybe I'll do the picture now. I guess, so this is what a k is going to look like. This, I think, would probably be just in the case where, let's say, r equals 4, let's say, and the kernel would probably look like that. Well, that would be, it would depend. I mean, let's suppose that, it's one that doesn't eventually vanish. So, so it's going to be, that's 0 there. It's symmetric, let's say, it's supposed to be symmetric. So it's, it's not negative, it's positive everywhere here. But then the tails, in the tails it's negative, and of course this is going to 0 here. Otherwise things aren't going to integrate out. Okay, so that would be a simple example of a higher order kernel. Right? So, that's not satisfied, of course, by the kernels we mentioned at first, and the ones which we intuitively, we might think of using, but we can reduce the bias by using, these other higher order kernels. And then how do we choose them in practice? Well, let's give, that comes up then in the next slide. So let's suppose, for the case r equals 3, let's say, I've introduced the concept of a kind of mother kernel here, which is a kernel which is, non-negative, and a kind of obvious one that we've introduced before, like the normal density or the uniform density. The uniform density was the flat one, and then there was the normal one. So those are, of course, not higher order kernels. They're always non-negative, but we could say, well, let K be C plus du squared times phi of u, where phi is the standard normal density. So phi is is of course one of the possible choices of K, but it's not a higher order kernel. But if we have that factor in there, we have to satisfy two properties then, for choosing C and D. We have to have the kernel integrating to 1 still. We still want that property, all right? If we don't have that property, then the expectation of f hat will not converge to f, it will converge to f times some multiple, all right? So that's what, we have that property holding throughout. But then we also have the integral of u squared times k0. That's this coming from this assumption that we made here, this is assumption 4. And so, we work this out using the properties of the normal density. Integral of, obviously, integral of c times phi is just c, and the integral of phi is 1. And then the integral of d times u squared times phi is just d, because the integral of u squared phi is just the variance of the standard normal, the second mode of the standard normal, which is 1. And then, likewise here, this is the second property, which is the higher order kernel property. Again, for the same reason we get this is c, because the integral of u squared phi is 1. And then we get a 3 here. This is because we have the fourth moment of a normal coming in. Fourth moment of the standard normal is 3. Right? You have to believe me there. Okay? So you just solve that out, and you get 3 over 2 and d equals minus a half. And in fact, that density will look like the picture that I had. Right? So you can see that the d coefficient can be negative, so that will sometimes predominate and give you a negative value. So that's enough for the kernel, for the higher order kernel in terms of the properties. But there's a reason for doing this, and that's because these are useful in the semiparametric material. Again, proving all this is complicated, but one can give some intuition why this property is useful. Now, Dr. Helmrich mentioned the importance of consistency, and so let's look at that now. And what is consistency? Well, there's different modes of consistency, and I think the most standard one in econometrics is convergence in probability of the same theta hat as before. So theta hat is a function of n. Okay, just like in my little introduction to talk about asymptotic and unbiasedness. So if for all epsilon, arbitrarily small epsilon, positive epsilon, the probability that theta hat minus theta is bigger than epsilon absolute value, that converges to 0 as n goes to infinity. So what it's saying really is like the distribution of theta hat is collapsing onto the point theta. All right? So it's a different property from asymptotic unbiases. In fact, you can have this holding without asymptotic unbiases because there's no assumption that theta hat has any moments. You may not have an expectation. On the other hand, it's certainly also true that you can have asymptotic unbiases without consistency. All right. So again, this is something that that causes confusion. And when we have consistency, I write it like that. There's numerous other notations. Theta hat with an arrow and a P for conventional probability. Okay. There are other notations. Easy sentence. Now, this is it's quite a complicated property, isn't it? Because you've got this idea of a small epsilon and so on, which is always a difficult thing. You need to have some knowledge of real analysis to do that. And I think it's important to stress that one sufficient condition for consistency is convergence in, if you like, mean square, which sometimes you can't do this actually, but if you can, it's a nice way of proving it. So the expectation of theta hat minus theta squared equals 0, that tends to 0. And what's happening there is that, you see, that's the mean squared error, because theta is not necessarily the expectation. So the mean squared error is the variance plus the square of the bias. So for that mode of consistency, which is the stronger one, you need both the variance to go to 0 and the bias to go to 0. All right? But that's rather more than you need for the basic property. But the fact that variance goes to 0 is again stressing the fact that somehow things are collapsing onto a single point. There's no variation in the limit. So they're different properties. So this is very important because consistency really is like a minimal property. Okay, then I have a little qualification, stressing the fact. Oh yes, now this is important though. As I said before, we can't always take expectations. But from Slutsky's theorem, it's supposed to be interested in a ratio statistic, and this is relevant here clearly because the Navarro-Watson estimate is a ratio, all right? So we can't say in general that's asymptotically unbiased, but if we can look at the numerator and the denominator separately and show that they are consistent for something, okay, and the denominator converges to something that's non-zero, then the ratio of these converges, to this limit. So that's obviously very nice, and that's important here directly for this Navarro-Watson estimate. All right, it's a special case of so-called Slutsky's theorem. So what I'm going to do now, again, I'll revert to looking at a quite general statistic, with we've got a general vector x consisting of y and z and so on. So it's all quite general. What we have, and again, I've got the theorem and the conditions. No proof, but I want to discuss the conditions. And so, all right, so the conditions of theorem 1 are all holding, okay, but the L is replaced by K, and so we have big L equals 1. So we don't have this L factor coming out, capital L factor. All right, so now I think probably the most notable additional condition here is that the x's are independent. And this is really very important for proving consistency, because what it means, when you've got independence, you have accumulation of information, a lot of accumulation of information as n gets larger, because each x is independent of the previous one, so it's giving more information. If they all, were perfectly correlated, you say, or they were xi was equal to the same random variable x for a while, you wouldn't get that. You'd have extreme dependence. If you got the independence, this is very important here for the convergence in probability, because of that increase in information, the variance is going to go down to 0. So that's probably the most notable innovation here. We're ending up with this convergence in mean square, which is the one I mentioned when the expectation, perhaps I should stress this again on a piece of paper, that what this property means is that tends to naught. Okay, that's convergence in mean square, and that's an easier property to prove than just convergent probability. It's a stronger property, but it's kind of simpler to prove. It doesn't involve introducing these epsilons and so on. It'll involve stronger conditions than we need for convergent probability, but it makes life a bit easier, and maybe the extra assumptions are not too onerous. Okay, just to stress, I know I mentioned that convergent probability is implied by, that kind of thing, but just to stress what we mean there. Okay. All right, so let's go back again. So this second assumption, that's rather like the smoothness assumption we had before, but we need, because we're squaring things in this convention, that's why we have the exponent of g squared there. Likewise, we have the second moment condition. This is obviously stronger conditions, but they're not too onerous perhaps. Also, we need that to count the square integrable. This is again a minor condition that we're going to know whether it's true or not. We're not going to choose a kernel that doesn't satisfy that. We can easily check that condition. Now, this condition is important because remember we said that A goes to 0, or in which if A is a matrix, that means all the elements of A go to 0. However, it's saying that n times the determinant of A goes to infinity. So A can't go to 0 too fast. And what this is then saying, this is really saying that, when we're talking about asymptotic unbiasedness, we want A to be small because we don't want the effect of neighboring points to be, where the function is different, to be too great. I'm getting the microphone gain. I would just sort of attach it to myself or something. That would be better, wouldn't it? For consistency, if we had these pictures up here where we stress the fact that you need a reasonable number of observations to get good precision, and so if you choose A too small, you don't get that. So this is really telling us that for the consistency to get reasonably precise estimates, for the variance to go to 0, you need this property. And this is kind of almost a minimal condition really almost throughout the literature. Almost any property you're concerned with, apart from asymptotic unbiasedness, you're going to need something like this. So, say there any. All right. So we can have a couple of corollaries here then from this result that under the conditions, we get convergence in mean squared, therefore in probability of the density, kernel density estimate. And then also, we look separately, show consistency in numerator and denominator, use Slutsky's theorem. This will converge to P of Z, this will converge to F of Z, and P over F is just the H of Z, or this quantity. So there we are. So we've got consistent estimates of those. All right. And this is under pretty mild conditions. As I say, it's not easy to get rid of this. Now, have I got time to talk about choice of boundaries? I think probably I just about do, so I'm not going to run too short of time here. Now this is a bit of light relief in a sense, because here we're going to be more heuristic. I know I'm not giving proofs anyway, but we have these mathematical conditions. But how do we choose the bandwidth A in kernel? This is always important, because you have to do this. You've got a given data set. You have to say, you have to choose a kernel, you have to choose a bandwidth, and there is sensitivity. Right. Now there are different philosophies to this, and I have a certain point of view, but let me look at different kinds of approaches. Now, theorem 2 is partly motivated by higher order kernels, but it's also useful for when you haven't got so much smoothness and you have an ordinary kernel. Because as we said, in that case, when r equals 2, you get a bias of order r squared. So, in fact, to be a bit more precise than in that result, for the density estimate, just the scalar density estimate. And again, I'm just going to look at this for the simplest possible setting. Because similar principles apply more generally, but we don't want to clutter things up too much. Looking at, basically, it's like a Taylor expansion kind of thing. This is like one is an approximation. You can see the most important point is the A squared here, as A goes to naught. But we've written a couple of extra factors here. This one, depending on the kernel, and this one, which is the second derivative of F. All right? Because actually there's a term in the middle, which is 0, which vanishes in the first derivative, it turns out. So that's why, that's the reading. This is really 2 factorial from Taylor expansion. So if this is a continuous function, say, the bias can be made arbitrarily small by picking A small enough. On the other hand, now this is really coming from from theorem 2, or the proof strictly speaking, but it's kind of must be the case because we said that f hat is going to be consistent, in mean square. The variance of f hat, it turns out, by looking at things a bit more closely, will behave like this. Kappa was the integral of k squared, all right, which was introduced as one of the conditions. F is just the density itself, which we're trying to estimate, that it arises in variance. And we get in the denominator, we get this NA. And this, of course, illustrates why we need NA to go to infinity. Because we want this variance. We must have this variance go to 0. All right? So that explains, to some degree, why we need that kind of condition. The point is, though, here that the main thing is the dependence on NA. So this is the order 1 over NA if you ignore the other factors which are bounded. So on the other hand, we make the variance smaller by increasing A, not making it too small. so that on the one hand, the bias, this is what I mentioned to begin with in a more vague kind of way, is that there's a conflict here. We make the bias small by making A small, but then that increases the variance. Likewise, if we make the variance small, we don't want A to be too small, but then the bias may be large. So what do? Well, the mean squared error is the answer here, and for the most part, when people look at the choice of A in a kind of a fairly mathematical way, they look at mean squared error. So the mean squared error of f hat is the variance plus the square of the bias, and that's approximated following from what we've just said by this quantity here, where we're ignoring any higher order terms. C1 over NA, where this is C1, C2 squared, the square of C2 times A to the fourth, because this is the square of the bias. Bias is order A squared. Well, we can choose to minimize the mean squared error. So if we differentiate with respect to A, I won't go through all the details, but the solution here, you get this quantity where you've got this big factor here. But the main point is that the order of magnitude is 1 over n to the 1/5. Okay? So that's called like an optimal bandwidth, and the n to the 1/5 is an optimal rate. But that doesn't get us, too close to actual bandwidth choice in practice. Of course, one other point is that C1 and C2 vary with x. And in practice, if we want to compute things for a range of x, we don't want to have to worry about choosing a different bandwidth for each x point. Actually, some of the literature does. You can do that, but it's a lot more effort. So one thing, and I'm going to have to finish, I guess, probably before finishing this section, but what we sometimes do then is look at, instead of the mean squared error clipped individual points, we integrate out x, and we look at the mean integrated squared error. And if we integrate out the formulae we had before, essentially we get this kind of thing where we get some factor c, which is this, where we've integrated out over x, essentially, times n to the minus fifth, the same one as before. So that's a bit more manageable, isn't it? We don't have to choose things for, to change the choice of bandwidth for each x. My watch again is a bit slower than the clock, so shall I? It's better, is it? Okay, I'll go on a little bit then. Well, now the thing is, though, both these optimal bandwidths, whether or not you determine or not, do depend on the unknown f. So here, the second derivative of f. Well, we don't know f, of course, so we clearly don't know the second derivative. I mean, the whole point here is to estimate f. And it's inconceivable that we would know the second derivative function when we didn't know the function itself. So there's no way we're going to know this. So we can't actually implement this. This is no problem. We can evaluate this. Kappa is just the integral of k squared, so we can evaluate that. No problem at all. But this is a problem, right? So we cannot compute that optimal bandwidth. So what do we do? Well, this is just different strategies here. It's pilot estimates. In other words, we could say, well, let's suppose that, let's take f to be the normal density and evaluate these quantities, like the second derivative, integrate out. We can do that quite easily. You can actually get quite a simple formula. And that may be reasonable. You know, if the actual density is not too far from normal, let's say, it might be reasonable. Oh, sorry, no, that was the second choice there. Okay, but give the parameter one. The other idea is to plug in estimates based on an arbitrary bandwidth. So in other words, in particular, you know, we've talked about estimating derivatives, haven't we? So you could imagine you could get a kernel estimate of the derivative at different points x, and let's say approximate the integral by a sum. You know, so you could approximate that. It's quite a bit of work to do, actually, isn't it? But you could, in principle, do it. I don't think many people do that, though. Or you could, I mean, what you see this suggested in some sources, textbooks, and so on. It said, well, let's just choose an arbitrary constant c. But the trouble is that you know, choosing c to be arbitrary is really just the same as choosing a to be arbitrary. So it doesn't make much sense. I mean, sure, you say, well, let's take c equals 1. Okay? But not really common sense. It's just arbitrary. The only thing where that would be useful, probably, is if you were doing Monte Carlo studies and you wanted to see how things varied as you changed n. You kept the c fixed and you let n increase. You know, that idea might be worthwhile. Okay. Well, the other idea, and I mentioned this before, that you know, intuitively, the larger the variation, like the variance of x is, that the larger a should be. You imagine you've got data, you know, these x's, and you decide to multiply them all by 2. Well, intuitively, you should really multiply the bandwidth by 2, shouldn't you? Because you're increasing the spread of the data. So you could use a simple scale estimate, such as the sum of the standard deviation. Again, though, it's somewhat arbitrary. It's, you know, it's not an optimal thing to do. You can extend all this theory to the multiple multivariate PDFs. The theory doesn't quite work for kernel regression estimates because of their ratio form, don't have moments, but you could justify things in an approximate way. I think I should probably leave. Oh, no, let me just do this slide before I. Is it okay? Shall I just go on with it? Because the next section is cross-validation. Yeah, let me just finish off this section. So this isn't too important. We can extend this theory to use greater smoothness in F. So using theorem 2, if R is some other number like 6 or something, we get this result, you know, where we've got the bias of order 8 and 6, something of smaller order. The mean squared error then will have the same kind of variance, same order, but the bias will be even smaller. And there the optimal A has a different rate, also a different factor, but the rate is -1 over 2R plus 1. So in other words, if you have greater smoothness, you should choose A to be larger, which makes sense, doesn't it? Because you know things are not varying so much. You should use a wider range. So you know, if R equals 4, let's say this is n to the -1 over 9, which is you know much bigger than n to the -1 over 5. So you can do this. I mean, the majority of the literature looks at this case where the optimal rate is n to the -1/5 big factors. On the other hand, you can even choose an A of smaller order. For example, R equals 1, then you get a rate of n to the -1/3, which actually does sometimes arise n to the -1/3 rate, naturally in other cases I've found this in my research. So this is just intuitive. It makes sense, obviously, to vary the smoothness of F. If it's very smooth, we borrow information from other parts of the distribution. If it's very unsmooth, this practice can lead to serious bias. I mean, actually, I haven't stressed this here, but my preference, if you're doing Monte Carlo studies, or if you're doing empirical work, rather than trying to use some kind of optimal bandwidth, like the ones I'm talking about, or the cross-validation, which I'll discuss next time, I would tend to often to compute things for perhaps some grid of values of A, you know, maybe 4 or 5 or more, and see how sensitive things are. You know, sometimes there may not be great sensitivity, sometimes there will be. Obviously, if there's great sensitivity, then you've got to kind of worry a bit. But I think it's dangerous myself to just automatically, you know, use some particular method, you know, which may be in computer software, and people just use it blindly, and it may not give good results. And just because it has certain properties, they may not be very relevant. There's also other, you know, senses in which things can be optimal, the ones, you know, which are stressed mostly in the literature and in computer software. All right, well, thanks very much.
Any question? So we should thank you, teacher, for giving such a excellent lecture to our. Thank you very much.
Okay.